It was just poetic. As if it was meant to be. Like we just fell into the beauty of math.
No, terrible.
We always wanted to make YouTube videos about math. The summer math exposition was just the final motivation we needed. But we had collected so many ideas for math YouTube videos. So we got together to decide, but we really were undecided. We considered talking about the infamous Collatz conjecture, or making a video about math notation, or talking about Galois theory. At a certain point, we were considering talking about modular arithmetic. Modular arithmetic is a field of math that studies the remainders of the integer numbers when you divide them by some other fixed integer. Modular arithmetic is full of really cool theorems and ideas and concepts like quadratic residues or the Chinese remainder theorem. There is one in particular called the Euler-Fermat theorem that involves a really particular function called Euler's totient function, usually denoted with the Greek letter phi. This function takes an integer as an input and outputs an integer. If the input is n, so phi of n, counts how many numbers smaller than or equal to n are co-prime or do not share any prime factors with n. For example, let's count how many numbers smaller than 10 are co-prime with 10. 10 obviously shares a factor of 10, 5 shares a factor of 5 with 10, and 2, 4, 6, and 8 share a factor of 2. So the only numbers that are co-prime with 10 are 1, 3, 7, and 9. That are obviously smaller than 10. So in that case, there are 4 numbers, so phi of 10 would be equal to 4. The graph of the function looks like this. We were considering talking about this function, so we decided to graph it. We found a Desmos project with a graph in it, but it also had this. Now, our logical immediate reaction was, what the hell is going on in here? Why in the world would this thing on the right hand side, a really weird sum involving a greatest common divisor and the cosine function, a function that usually outputs irrational numbers, be equal to, in the first place, an integer number, and in particular, phi of n? When we were done losing our minds, we tested the formula. It worked. We googled the formula. We couldn't find anything. So we started thinking about it, trying to understand, trying to prove it. And we came up with an answer. So we have decided to walk you through our thought process when we were figuring this thing out. Not only because we think it is just delightful, but because we also think it exemplifies how mathematicians try to solve problems, how they try to build up their intuition from simple cases. We really encourage you to pause the video and give it a try. Try to understand the formula, and if you're feeling good, try to prove why it holds for all natural numbers. Now, buckle up, because the show is about to begin. We need to talk about complex roots of unity.
First, let's look at this equation. Seems boring, right? The solutions are 1, and if n is even, we also have -1. But what happens when we expand our search to the whole complex plane? To understand what happens here, we need a clear visualization of what multiplication means for complex numbers. If we see complex numbers as arrows in the coordinate plane, multiplicating a by b means stretching or squishing the arrow by the length of b as a factor, and then rotating the arrow the exact same angle that b makes with the positive horizontal axis. So finding an arrow x such that x to the n equals 1 means finding an arrow of length d and angle alpha such that d to the n equals 1 and n times alpha equals the angle 0. Since d is a positive number, it must be 1, but the angle is a bit more interesting than that. It turns out that there are many angles that end up in 0 after rotating them n times. And they look kind of nice because they end up forming a regular polygon. There's a really nice fact about roots of unity. They sum up to 0. Yeah, I know it sounds crazy at first that a bunch of arrows pointing anywhere end up summing 0, but it makes a lot of sense once we realize what this means at the end. Look at the figure formed when we go through adding all the roots. Also, roots of unity are the main attraction when we are talking about rotations and symmetry, so it isn't surprising that the sum of all rotations equals 0.
Among all the nth roots of unity, there are some of them that are special. We will call a complex number a primitive root of unity of order n, if it is a root of unity of order n, but it is not for any exponent smaller than n. So for example, -1 is a primitive root of unity of order 2, but it is not a primitive root of unity of order 4, it's just a root of unity of order 4. A nice property is that if we enumerate the roots of unity of order n, both primitive and not primitive, in counterclockwise order and ending in 1, the primitive roots are the ones such that their number is relatively prime with n. Primitive roots are important because each one of them generates all the other roots of that order by just raising it to the powers of 1, 2, 3, blah 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 up to n. Now, a totally natural question to ask is, what is the sum of the primitive roots of unity of order n? We didn't know the answer, so we googled and found a table with the first few values. We couldn't believe our eyes when we saw that these sums seem to be always -1, 0, or 1. Since we couldn't find any pattern in this seemingly random distribution, we tried searching it on OAs, and the result was just wonderful. This is the Mobius function. Have you ever heard about the Mobius function? We neither.
The Mobius function is an integer-valued function, just as Euler's tangent function, meaning it takes an integer as an input and outputs an integer. It is usually denoted with the Greek letter mu. The value of mu of n can only be equal to -1, 0, or 1. Mu of n will be 0 if n is a multiple of a perfect square other than 1. Something like it's a multiple of 4 or it's a multiple of 9. Or, what is the same, if its prime factorization has repeated primes. If n is not a multiple of a perfect square, then n is a product of distinct prime factors. If the number of prime factors is even, then mu of n is 1, and if the number of prime factor is odd, then mu of n is -1. But then, why would the sum of the primitive roots of unity be equal to mu of n? Well, let's study each case. What if n has a square divisor, or it's a multiple of a perfect square? For example, what if n is 18? Then 18 is a multiple of 9, which is 3 squared. The key fact here is that the prime factors of 9 are also prime factors of 18. Then, if some number does not share any prime factors with 18, then that same number won't share any prime factors with 9. So, if a number is coprime with 18, then it will also be coprime with 9. What this tells us is that the roots of unity will make a pattern that repeats each 9 roots. In other words, that you can group the 18 roots of unity into 3 groups of 9, and if you look at the primitive roots on each group, the pattern will be the same. I like to think of this as having a pizza and making 3 pizza slices and putting olives on the primitive roots of unity. Then the 3 pizza slices will have olives on there, and the olives will be in the same relative position inside each pizza slice. But now I could draw these triangles from these olives or these points in this way. Remember that these points represent the 18th primitive roots of unity, and we want to add them up. But now if we look at each triangle, well, they're just the 3rd root of unity just rotated, and we know that they add up to 0. So adding several times those triangles will just be 0. So the sum of all the primitive roots of unity will just be equal to 0. If n is a prime number, then Mobius of n, or mu of n, is -1, because, well, n has only one prime divisor, or one prime factor itself. So since 1 is odd, mu of n is -1. And if n is a prime number, how many numbers from 1 to n are coprime with n? Well, all of them, except n itself. Then the primitive roots of unity will be all the roots of unity except 1, the last one. And what is the sum of all the primitive roots of unity if n is a prime number? Well, give it a try. It's not a hard question. Just remember that the sum of all the roots of unity, including 1, was 0. But now we don't want to add the 1, so we just subtract it, and the answer will be 0 minus 1, which is, well, -1. For the last case, consider n is a product of distinct primes. For example, let's work with n is equal to 30, so n is 2 times 3 times 5. And what we're gonna do is, we're gonna add up the non-primitive roots of unity, because since the sum of all the roots of unity is 0, and we claim that the sum of the primitive ones is mu of n, well then, the non-primitive ones should add up to minus mu of n. So let's work with 30. What we're gonna do is consider all the non-primitive roots, and remember that a root is non-primitive if it shares a prime factor with 30. So it shares a factor of 2, 3, or 5. And we'll think of 30 as 6 times 5. So we're kind of factoring out the 5. So we're gonna split the non-primitive roots into 2 groups, the red and the blue. The blue ones are gonna be the ones that share a prime factor with 6. So they share a factor of 2, or they share a factor of 3. And the red ones are gonna be the ones that are coprime with 6, but not with 5. And notice that if you are not coprime with 5, since 5 is a prime, well then it means that you are a multiple of 5. First, let's start with the blue ones. Notice that the blue ones, well, they're just like in the last case, because I can group them in different portions that make like the pizza slices that we talked about. So I can draw hexagons from them. And the red ones, well, as I said, they are just the multiples of 5. And the key here is that the roots of unity of order 30 that are multiples of 5 are just the roots of unity of order 6. But remember that they were the ones that were coprime with 6. So essentially, the red ones are the primitive roots of order 6. And we know that they add up to mu of 6. So then, the sum of the primitive roots of order 30 is minus mu of 6. And we know mu of 6 is 1, so the sum of the primitive roots of order 30 is -1. And that is exactly mu of 30. The way the Mobius function counts how many prime factors you have helps us do this trick where at the end, mu of 30, well, it's just minus mu of 6 because it has one extra prime factor.
What is that cosine doing there? How can that be related to Euler's totem function? Let's see the formula working with an example. N equals 5. Why is that even going to be an integer number? If we calculate each term, we have a sum of some probably irrational numbers. Now, these cosine terms, they reminded us something familiar. They are the real part of the roots of unity of order n. If we look at the arrows that represent the roots of unity, these cosine terms are exactly the horizontal coordinate. But splitting the complex numbers into just one coordinate is a bit awkward. So let's see if we can say something about the vertical coordinate of these expressions. Each root is stretched the same length than its conjugate. So when we sum all these stretched expressions, the result will be real. This tells us that the formula will be exactly the same if we change the cosine terms with each corresponding root of unity, and this is something much simpler to work with. So we have these stretched roots of unity, and we want to see that the sum will be the totient function of n. Since the roots can have different lengths, let's first focus on the roots with the same length. For instance, the roots that were not stretched at all. These are the primitive roots of order n, so their sum is the Mobius function of n. If we then focus on the roots stretched by a factor of 2, we can notice something peculiar. They are the primitive roots of n divided by 2. This makes sense because if some number t meets the greatest common divisor of t and n equals 2, then t divided by 2 will be relatively prime to n divided by 2. So the sum of this group of roots of unity is the Mobius function of n divided by 2. Since they are also stretched, the sum in this context will be 2 times the Mobius function of n divided by 2. And so on. It turns out that this sum is a sum involving all the divisors of n and the Mobius function. So now what we want to prove is that the totient function of n is the same as this sum. Now let's see as an example when n equals 18, which values of t and n divided by t we can have. But wait, each pair appears twice, just that in the other order. But if we go through these terms backwards, we can say that the sum will be the same than summing n divided by t times the Mobius function of t. So in the end, we want to prove that the totient function of n equals this sum. This can be proven with an inclusion and exclusion principle. Do you remember what the totient function of n was actually counting? We are going to use the sum to end up counting how many numbers smaller than n are relatively prime to m. Let's assume, again, that n equals 18. If we look at the term of 1, we see 18 divided by 1 times the Mobius function of 1. Since the Mobius function of 1 is 1, we get 18, which can be seen as how many numbers there are in total less or equal than 18. When t is 2, we get 18 divided by 2 times the Mobius function of 2. Now, 18 divided by 2 is 9, which is exactly how many numbers between 1 and 18 are multiples of 2. And since the Mobius function of 2 is -1, we can imagine that this term is actually erasing the multiples of 2 of the set of 18 numbers. This makes sense because these numbers are not coprime to 18, so we don't want to count them. If we go on to 3, we get 18 divided by 3 times the Mobius function of 3, and again the Mobius function of 3 is -1, and 18 divided by 3 is 6, which is exactly how many numbers between 1 and 18 are multiples of 3, which we don't want to count neither. So this term is erasing the multiples of 3 of the set. But wait. If we erase the multiples of 2 one time, and then the multiples of 3 once more, it means that we erase the multiples of 6 twice? Well, yes. But this issue is fixed when we go on to the term of 6. Since 6 is the product of 2 primes, the Mobius function of 6 is 1, so in the formula it appears that we are summing 18 divided by 6, which is 3. That is exactly the number of multiples of 6, that are the ones that we erase it twice. Therefore, subtracting twice and adding once is the same as subtracting only once, so the multiples of 6 are not a problem anymore. If we apply this exact idea with every number, thanks to the way that the Mobius function is constructed, we will be adding and subtracting each non-coprime number the correct number of times, getting as a final result the number that are relatively prime to n.
It's kinda nice how we proved a formula that is stated completely under the real numbers by looking at it from the perspective of complex numbers and using them in our favor. A quite nice lesson to take from this amazing formula is that, as in almost every appearance of pi there is a hidden circle around, seeing terms like this one or this one is a clear hint to use roots of unity and rotations.
We think the process we went through kind of encapsulates the whole relation mathematicians have with good math problems. The first time you hear of a problem, you get this beautiful feeling of amazement. I always think to myself, oh my god, what a juicy problem. You automatically start working things out on your head, maybe try simple cases to build up your intuition. You try to understand the underlying pattern hiding behind the statement. If you are really moved by the problem, you start looking for a pen and a piece of paper in an effort to organize your ideas. And it might take hours, weeks, or years maybe, but eventually you come up with an idea that works, and you get this immensely satisfying aha moment. Unless you're trying to solve the Collatz conjecture. Yeah, that thing is just a monster. You feel so good that you want to externalize it. So you go and you text your friend super excited to tell him that you found the answer to the problem that you've been thinking of. And I don't know why, but the answer is always,
Yo, it's 3 a.m. Go to sleep, god damn it.